Good day. To this episode, we will be talking about sound waves. Sound waves are a type of mechanical wave that propagate through a medium. The medium is typically air. Waves are created by the vibration or oscillation of an object, which causes compressions and rarefactions in the surrounding medium. Any objects that vibrates can be a source of sound. This includes musical instruments, our vocal cords, and even everyday objects like the car engines. Sound waves travel in a longitudinal or compression wave pattern. This means that the particles of the medium move back and forth in the direction of the wave's motion. As one particle compresses, it pushes on neighboring particles, transferring energy through the medium. Sound waves require a material called medium to travel through. In most cases, this medium is air. But sound waves can also travel through solids and liquids. In space, however, where there is no air or any other medium, sound waves cannot therefore travel. The speed at which sound waves travel depends on the properties of the medium. In air, at room temperature, sound travels at approximately 343 meters per second. That is about 1,235 kilometers per hour or 767 miles per hour. When an object, such as an aircraft, can reach a velocity of the sound speed, such speed is called Mach 1. The Mach number is the ratio of the speed of a body to the speed of sound in the surrounding medium. Mach number 5, for example, means that it is 5 times faster than the speed of sound. Sound waves are also characterized by their frequency. Frequency means the number of oscillations or cycles per second. Frequency is measured in hertz with a symbol Hz. So that is, the higher the frequency, the higher the pitch of the sound. On the contrary, with a lower frequency, the corresponding sound is also lower pitch. With the use of detectors, sound waves can be visualized through an amplitude. An amplitude of a sound corresponds to its intensity or loudness. A greater amplitude indicates a louder sound. Amplitude is typically measured in decibels. Noise above 70 dB or decibels over a period of time may start to damage your hearing. Loud noise above 120 decibels can cause immediate harm to your ears. The formula for sound intensity in decibels is equal to the decibel number is equal to 10 times log of the intensity over the threshold of the intensity, which is the softest sound that a healthy human ear can detect. In this example, a sound has an intensity of 3 times 10 to the minus 8 watt per square of a meter. What is the sound level in decibels? Our formula, the decibel value is equal to 10 times log of that intensity over the threshold intensity, where that is the softest human ear can hear. And so we will substitute the equation I with the value of 3 times 10 to the minus 8 watt per square of a meter. And so, the final answer will be equal to 44.8 decibels. Another characteristic of a sound or sound wave is called the wavelength. The wavelength of a sound wave is the distance between two consecutive points in the wave that are in phase. For example, that is between two compressions or two rarefactions. Wavelength is related to frequency and the speed of sound. By equation, speed is equal to the frequency times its wavelength. So in other words, speed is the number of wavelengths that passes through a single point in every unit time.
The speed of sound increases with temperature, and that is 0.61 meter per second in every degree temperature increase. So the formula will be speed is equal to 331 plus 0.61 times the temperature degree increment. For example, an explosion occurs at a distance of 6 kilometers from a person. How long after the explosion does the person hear it? Assume that the temperature is 14 degrees centigrade. Because the speed of sound increases by 0.61 meter per second in every 1 degree Celsius, the original velocity is 331 meters per second. That will be added by the increment of 0.61 meter per second per 14 degrees. That will give us a total value of 340 meters per second. That will be our new velocity of the sound. Using the formula distance is equal to speed times time, we have the formula time is equal to speed over velocity, and so therefore the distance is 6 kilometers or 6,000 meters divided by 340 meters per second, and so that will be equal to 17.6 seconds. That is the time that the person hears the explosion at a distance of 6 kilometers. In this problem, a tuning fork oscillates or vibrates at a frequency of 284 Hz in air. We will compute what is the wavelength of the tuning fork when it is emitted at 25 degrees centigrade in the room. The speed of the tuning fork is equal to 331 meters per second plus an increment of 0.61 meters per second in every degree, and at 25 degrees added, that will give us a total speed of 346 meters per second. Using the formula lambda or the wavelength, that is equal to speed of the wave is equal to 346 meters per second divided by the frequency of 284, that will give us a wavelength of a meter and 22 centimeters or 1.22 of a meter. Do you know that the distance of lightning activity can be estimated by dividing the time interval from the flash of lightning to the thunder sound by 3? The distance is in kilometer. For example, when the interval time is 15 seconds, that will be divided by 3, and so therefore the lightning activity is approximately 5 kilometers away. For example, there are two tuning forks that are sounded simultaneously. They both produce 1 beat in every 0.3 of a second. By how much do their frequencies differ if we are going to put a piece of chewing gum and place it on the prong of one of the tuning fork? That's specifically the second one. Now, the other tuning fork will now beat 1 beat in every 0.4 of a second instead of the 0.3. was this tuning fork having the lower or the higher frequency. Now we are going to make use of the formula of frequency, that is the number of beats or vibrations or oscillations in every second. For the first tuning fork, that is 1 beat or 1 frequency vibration in every 0.3 of a second, and that gives us 3.3 Hertz. So that will be the frequency of the first tuning fork. The second tuning fork will only beat 1 vibration in every 0.4 of a second, giving us 2.5 Hertz. So by adding the gum to the prong of the second tuning fork, this increases the mass of the tuning fork, and so therefore will produce the lower frequency.
Another characteristic of a sound is the Doppler effect. The Doppler effect describes how the frequency of a sound wave changes as the source of the sound or the observer moves relative to each other. The Doppler effect is also responsible for the change in pitch of a siren as a vehicle passes by.
Doppler effect formula is equal to V plus V sub O over V minus V sub S multiplied by F, where F prime is equal to the observed frequency and F is the actual frequency, while V is equal to the velocity of the sound waves and V sub O is the velocity of the observer and V sub S is the velocity of the source of the sound. In this problem, there is an automobile moving at 30 meters per second is approaching a factory whistle that has a frequency of 500 Hz. If the speed of the sound in air is 340 meters per second, what is the apparent frequency of the whistle as heard by the driver? Repeat for the case of the car leaving the factory at the same speed. First, we are going to determine the apparent frequency of the whistle as heard by the driver. Using the Doppler effect formula, the speed of sound in air is equal to 340 meters per second plus the speed of the observer, that is the automobile, which is equal to 30 meters per second, that is divided by the speed of sound in air, that is again equal to 340 meters per second, subtracted by the source of sound, which is equal to 0. And so therefore, the apparent frequency of the whistle as heard by the driver is equal to 544 Hz. And so this time, we will do the repeat for the case of the car that is leaving the factory at the same speed. Again, the frequency of the whistle is equal to 500 Hz, and the speed of the sound in air is equal to 340 meters per second. And since the observer is already going away from the source of the sound, we will put minus 30 meters per second. Altogether, divided by the speed of sound in air, again that is equal to 340 meters per second, minus 0 because the source of sound does not move. And so the apparent frequency of the whistle as heard by the driver is equal to 456 Hz. And so therefore, when the car is moving towards the source of the sound, the apparent frequency of the whistle has a higher frequency, which is equal to 544 Hz, while the apparent frequency of the whistle as heard by the driver when the car is already moving away from the source is a much lower frequency, that is equal to 456 Hz.
Like light, sound waves can be reflected of a surface, like an echo of a canyon wall. Sound waves can also be refracted or bent, that is, when they pass from one medium to another, such as from air to water. Understanding the science of sound waves have numerous applications in our daily lives. That includes communication in speech and music, medical imaging such as ultrasound, sonar systems, and various forms of entertainment such as movies and concerts. Understanding the properties and behavior of the sound or sound waves is also essential in the fields of physics, engineering, music and acoustics, as well as in practical applications like sound engineering and noise control.